Hi, everyone. Thanks for coming out tonight. I want to welcome you all to this month's not Kubernetes, SRE meetup. I'm Trish Crane. I'm a technical program manager here at Squarespace. So tonight we have two talks for you. We have Romanyak on our Squarespace team, who is our network engineer. He's going to be talking about Squarespace's Clos Datacenter fabric. And then we also have Martín Beauchamp from Shapeways, who's going to be talking about G.I.F.E.E your network. So thank you very much. Take it away, Roman.
Check. Hey guys, my name is Roman. I'm a network engineer at Squarespace, and this talk is about Squarespace network evolution over the past couple of years, and also about spine and leaf network topology that we recently built. I'm going to talk about mostly 2 layers out of OSI 7-layer model, physical data link and network layers. So traditionally, we were building layer 2 networks based on layer 3 model consisting of access layer, aggregation or distribution layer, and core layer, right? So everything was layer 2 on the access layer. We had VLANs on every access switch. We were running some redundant gateway protocol like VRP or HSRP for Cisco, and core layer for routing in between the pods. So this network was actually, this type of network was not too stable because of could get not too stable because of potential layer 2 loops or broadcast storms, or it would be easy to break. One of the variations of the layer 2 topologies that we at Squarespace had is collapsed core, when we had our aggregation and core layers collapse into one set of core switches, and these core switches were basically aggregation point for top of rack switches, which were purely layer 2. We also used some proprietary techniques and features to make appear our core layers to top of rack switches as a single switch. In this case, it's MCLAC from Juniper. So it's a proprietary protocol that is, it's easy to understand while you're working on it, and then it's kind of easy to forget when you have to troubleshoot it. So let's say in this case, when a host in VLAN RAT wants to talk to the other host in VLAN RAT, it's going to initiate a broadcast to look for the ARP, and that's going to go to all switches in the network that has that VLAN. As I said, it's the disadvantages of this network setup is layer 2 everywhere, STP, slow convergence, and scalability. If we run out of ports on core switch, we need to either do a maintenance window and be very careful to insert a new line card, or we have to replace the device, or we have to build a new pod and basically readdress everything, or allocate a new address space and move on. So we need something that we could scale, that would scale horizontally, that will have a limited set of features and not use anything from proprietary vendor protocols or features that would lock us into using one vendor. We would also want to minimize our broadcast domain and make the network more stable. we looked into building the spine and leaf layer 3 network based on Clos, where scaling is just a matter of adding more spines, and increasing the capacity would mean just add more spines and add more uplinks to the leaf and watch the over subscription ratio. Yeah, that network wouldn't have, the spine and leaf network wouldn't have any STP aside from the local STP on the individual switches. And we need some kind of routing for that network. What choices did we have? We could use OSPF or ISIS as a traditional IGP, or we could use something else that would gives us more control and it would be easier to automate. And we looked into using BGP as an IGP, and in the internet there were a lot of presentations how other people did it. The first one was Alex Lapujo from Microsoft, who actually presented it in 2011, how he built a layer 3 network on BGP only at Microsoft. So we looked into that. We decided to use BGP as IGP. Right before drilling into BGP as IGP, I just wanted to mention that BGP is used in the internet for decades, and it's proved to be stable, and it's used in the internet to route between autonomous systems. This is, for example, the screenshot from Hurricane Electric, where you could see how Squarespace is connected to the internet, and you could log into any route BGP Looking Glass and do show route and see how you could route to Squarespace. Back to spine and leaf. All right, so within BGP we had two options: to use iBGP or eBGP. Right, so iBGP is basically when all your switches, all your network is in one autonomous system, and you have internal BGP sessions between leaves and spines. BGP is using a couple of rules for loop prevention. One rule is if the router sees its own autonomous system in the route, it's going to reject it, and also the iBGP speaker will not advertise routes learned from one iBGP speaker, a neighbor to another one, right? So in this case, the spine switch has leaves as its neighbors, and it's not going to advertise routes learned from the leaf to other leaf, unless you convert the spine to be a route reflector, but route reflector reflect only best route, so load balancing will not be supported by default, and you have to enable add path feature in BGP, which is not supported everywhere and by all vendors. And it's like more complex, right? You have to remember that you have to do route reflection, you have to do this add path feature. And for example, in Juniper, in VRF, add path is not supported, so you can't use it there. So eBGP as opposed to iBGP is an obvious choice here. A separate private autonomous system number is assigned to every leaf and to every spine, to every switch. And then we had to think about addressing the whole IP space, of the loopbacks, of the point-to-point links. So point-to-point links would not be routed. They would be needed only for BGP session between the leaves and spines. And yeah, and that's it. Very simple. ECMP is supported on any switch. Maximum is like, right now it's 16 hops, I think. So you could load balance with this design very easily. And I wanted to show a quick video how well, I'll do it a little bit later when yeah, so video is going to be later. So eBGP, and then we could also use route servers here. We could connect the server to the leaf, physically connected to the leaf, but build BGP sessions to every switch, and we could do some traffic manipulations through the route server. We could, for example, black hole some network or subnet. We could drain a spine. Let's say we want to do a software upgrade on a spine. We could leverage the route server to send some routes with specific BGP communities to all switches, so they would avoid sending traffic to the spine. One of the requirements of the spine and leaf network buildup was automation, because it's really hard to configure everything manually, right? We have a lot of point-to-point links. We have to allocate every point-to-point link. We have to configure it, connect it, configure it. We have to remember where is, it's probably impossible to do it by hand, or it's going to take a long time. So we come up with we use Ansible to do automation in the network, and just to spin up the whole spine and leaf network, only one config file is needed, and this is an example of it. So we define IP space that we're going to use, the loopbacks, the service pool, some route server related information, and here on the right side we describe the switches. So in this example we have 2 spines and 1 leaf, and based on this we are building the network. So before actually lighting up the network, we had everything racked and connected, and all the switches were configured only with management IP addresses. And after running the spine and leaf playbook, the whole network was up and running and ready to take traffic. And in this video, I'm going to show how we spun up 2 leaves in our New Jersey data centers. So at that point, we had spines and a couple of leaves, and we wanted to light up 2 new leaves. So here I show that there is no BGP running on the switch. The interfaces are not configured, only management IP is configured. And show route, there's no BGP routes, only static routes to some management services. The spine was already built and had some leaves connected to it. So that's the spine with leaves. And here I start the ping to the loopback IP of the leaf switches. So when the switch is built, the loopback will be up. The way we do automation, we first build the config locally on the server, and then we run a second playbook to deploy the config that was built. Fast forward. So the config was built, and now we're going to deploy it, but first run dry run with -- check flag. So this is going to do, on Juniper, is going to do commit confirm and generate the diff file, and then we normally review diff files before doing the final push. So deploy commit check was finished, and now we check diff files. So that's the config for the switch, for the leaf switch, generated from that config file that I showed in presentation. All right. Yes, the interface section, the BGP section, BGP community section, VLAN section. And this playbook is going to push the configs to the switches. Show BGP summary on the leaf has 2 sessions to the spine switches. And ping is working now. And we have BGP routes to other leaves and to other networks. Yeah, and these are the routes that we announced to the spine switches. Okay, so what this layer 3 network with BGP on it gives us is what it doesn't give us. It doesn't give us the ability to move VMs from one rack to another rack, right? Because every rack has its own IP space allocated, so that's a disadvantage. But you can kind of address that by running by enabling the BGP between the server and the leaf, and there are a lot of solutions to do that: Quagga, BERT, ExaBGP, and others. So we can, we can configure, for example, if we have a couple of LDAP servers in different leaves, we can have these LDAP servers advertise the loopback IP, which is the same loopback IP, to the leaves, and it's going to load. We can have the same IP everywhere on every rack or on some racks, and it's a high availability solution, and it also can be used for the IP mobility. We can also build our own private cloud on Kubernetes, for example, Kubernetes and Calico, where kubes run BGP sessions with leaves, and normally kubes advertise two or more subnets, one for the service pool, and another one allocated for the kubes. So that's the things you get in layer 3 network as opposed to layer 2. In this slide, for example, it's taken from the show route command taken on the spine switch, and it filtered by community that belongs to Kubernetes routes only, and we could see that the first route is the service route announced by 3 cubes, because it goes to maybe three or more, but it's basically originated in 3 different leaves. And in addition to this route, we have individual cube routes originated somewhere, but we could tell where they were originated by the AES path. So if base ASN for leaf 1 is 64,811, then 812 is leaf 2, 813 is leaf 3. So this is leaf 3, this is leaf 5, this is leaf 6, and leaf 4. Yeah, that's it.
Thanks, Roman. Any questions?
Hi. I have one question regarding BGP, if you will, convergence. Maybe not really convergence, but it's, in my experience, especially in Juniper, when BGP connectivity is turned down, it takes some time to reestablish. And from what I heard, and I believe there is no way to adjust this timer. So you have to wait sometimes like 60 seconds or so for BGP session to be reestablished. Did you find any ways to overcome this? Or do you see this in your network? Maybe I'm doing something wrong in mine.
I cannot tell you how much time does it take for BGP to reestablish, but I don't think it's a huge deal to wait 60 seconds if you have redundancy.
That makes sense.
Yeah, so we use BFD to fail fast, to have a sub-second. I noticed that it takes longer time to reestablish BGP with the cubes between BGP and Kubernetes boxes. It takes longer time than to reestablish BGP, for example, between spine and leaf. It happens definitely sooner than 60 seconds, but I will have to check. Thanks for the question.
Okay, thank you.
Any other questions? No? Okay, thanks, Roman.
There's one more.
Oh, sorry,
There's
one more? Oh.
It looks like you automated the configuration portion to push the config, but as far as the IP address variables that you put in there, is that automated? Is that automatically created from the pool that you created on the NJ pod A, or is that manually kind of put in there as a variable? Is there an automation piece from like the pool to the config?
So depends which ones. Manually, we allocate manually the supernet for the spline and leaf, and then, for example, in this case, 10.160.0.0/14, right? And then for the leaf, we allocate the following fashion: that leaf 1 is 10.160.1.0, leaf 2 is 2.0, leaf 3 is 3.0. So like if you see it, the IP address 10.163.100, this is rack 3. Yes, it's predetermined, and the formula is like built in automation script. Also, you see the VLAN base 3000. It's also like we define the VLAN base, and then even though VLANs kind of don't matter in this case, but we configure a unique VLAN on every switch just in case maybe, you never know. Yes, so rack 1 is VLAN 3001, rack X is 3000X. Also, ASN, also AS number, private AS number is also predetermined, but everything else you don't do manually. Yeah, so there are some things you do manually, some things you automate. But that's why the config is pretty short, because everything is built. Yes, you need something to kind of base information, and then you can build on it.
Anything else? All right. So just give us a few minutes. We're going to set Martín up please help yourself to more beverages.
Thank you,
and
guys.
food, and we'll start in a couple minutes.
That?
I said I'm going to cross my fingers.
Oh, yes, thank you. Appreciate that. I think my password, I just got over the hardest part. Okay. Yeah. Yeah, relatively speaking.
Someone, I think she left there about Yeah, I think she probably left.
Was she
No, she was in operations.
Oh, okay.
She was like my, in a lifetime ago, we were both in publishing.
Yeah, okay.
And so she was my mentor when I went from.
Oh, she was the VP. Yeah.
Yeah, I forgot her actual title.
Yes.
VP something.
Yeah, she was great. She works here now?
No.
Oh, you worked together at
We
a
worked
past-
together.
Yeah.
last night.
Yeah, she was awesome. Yeah.
She was like my mentor for from the cousin we were both in.
Yeah, she ran like the Kindle stuff at Amazon before Shapeways. Yeah.
She was running, I forgot.
Yeah, she's awesome. Sad to have her go.
I know.
Hi, I'm Charles. Good to meet you. Nice to meet you. I think we might have talked to each other on DevOps Slack.
Oh, yeah, you just joined the
Yeah. These guys are doing Shapeways.
I have the whole crew here.
That's not bad. It's farming down here. How did I get along? Gotta get anyway. Yeah.
All right, is everyone almost ready to rumble? All right, I'm going to get started. So my name is Martín Beauchamp. I'm a site reliability engineer at Shapeways. And thanks to the Squarespace crew for inviting me to speak today. I thought my talk would fit in perfectly here. Over the last couple months, 3-4 months, there's been some great meetups about Kubernetes on bare metal, which is what Squarespace does. And that's also the direction that possibly Shapeways is headed into, maybe someday. So let's talk about what we're doing at Shapeways. So the title of my talk, Clos Networks for Data Centers, G.I.F.E.E. Your Network. G.I.F.E.E. stands for Google's infrastructure for everyone else. In this case, it's like Google's and Squarespace's and Microsoft, and a bunch of people are starting to do this. A little bit about Shapeways. We're the world's largest 3D printing service, community, and marketplace. This is a ring that actually goes on a finger somehow through there, designed by one of our community members, and it gives you a little bit of an idea about some of the cool things that people are doing at Shapeways. About our computing infrastructure, we have 2 physical data centers, one in New York City and one in Eindhoven in the Netherlands. We have our colleagues from the Netherlands here with us tonight, Hans and Wolf, also Paul and Puneet. You're gonna hear from him during the Q&A section. He likes doing the A. Sounded weird. We have 3 racks of servers. Take this mic from me. We have 3 racks in each data center, and we also have workloads in AWS. And some of our workloads go back and forth depending on utilization between our our data centers and AWS. There are about 7 of us in total, and the network I'm talking about has been in production in our primary DC for about 1.5 years and our secondary for about 1 year. Okay, so some of this stuff Roman covered quite nicely, so I'm going to go very quickly through it. If there's a topic you'd like to ask questions about or argue with me right here and now, put your hand up and we'll go in depth there. Okay, so we have the old way. Sucks. Roman talked about a great number of problems with it that we all agree with. The advantages of the old way, plug and play, right? So you plug something into layer 2 and it just works. All the servers talk to each other like magic, as long as you or some DHCP server have given them an IP address. And another advantage that should never be discounted is it's familiar to most of us. And if it's not, there's a very short learning curve. So if you don't understand how layer 2 works, 2 days later, you're an expert. Okay, so yeah, some disadvantages. It's hard to maintain the core switch stack. It's a god box. It has poor maintenance and failure modes. If it goes away, so does your data center. Bandwidth constraints are like baked in from the start. It doesn't work great for west to east traffic. So servers in region A, if they want to talk to a server in region B, they have to go all the way to the top of the stack here, and they're constrained by that center link. In the middle, if you run out of bandwidth there, you cry. Okay, so then there's poor vendor interoperability. If I had to have these two guys work together as my core switch in production, I wouldn't sleep very well the night before. So goodbye to competitive quotes for gear. We're effectively locked into one vendor because no one's actually going to do this. Right? Okay. That'd be a good chance to raise your hand. I did it. It was fine. Okay. So then unless we've done special work, our failure domain is the whole data center. And this was us, specifically me with the hat on. This is security footage from our primary data center when we were doing some routine thing that should have been fine, but wasn't fine. And it was not our fault, I swear. Okay, so Clos topology. Roman talked about this as well. But I have a pop quiz here. Who can spot the problem with this slide? Don, you saw this talk already, so you're disqualified. Okay, no takers. Clos is the name of a person. It is not an acronym. So here's Charles Clos. I could not find this person's picture on the internet. But he first formalized the Clos topology, it's named after him, at Bell Labs in 1952, which is over 60 years ago, which makes this the older of the two topologies between the two being discussed tonight. So this is not a new idea, but it's found a relatively new application in data center networking. So let's see, are there any things that Roman didn't tell you about why it's good? We have two trees here, a blue tree and an orange tree, and the nice thing is that they're independent. He talked about equal cost multipath routing, ECMP, which allows us to have redundancy for failover scenarios, but also double the bandwidth from a leaf to another leaf. Roman talked about the fact that you can use lots of different protocols to do Clos topology, and that will also give you ECMP, which is desirable. We also settled on eBGP for a lot of the reasons Roman talked about. So more good stuff about Clos, great scalability. I can just keep adding racks until I run out of ports on the spine. And I'm not increasing hops going for west to east traffic. Intra data center traffic still is 1, 2, 3 hops away, whether I'm going from rack 1 to rack 2 or rack 1 to rack 24, whatever. We can scale up. We scaled up the number of racks before. In this case, we're scaling up the available bandwidth. We're going from, let's say, these are 100 gig switches. We're going, in the previous case, we had 200. Now we have 300. We only had to buy 1 extra spine and, like, yeah, a lot of links, but whatever. And another great thing is the spine can go away. In this scenario, spine 1 died, and we lost half of our bandwidth, but importantly, not all of our bandwidth. So as long as our normal utilization's below 50%, we're fine. If it's above 50%, it's time to buy a new spine. And I'm only constrained there by the uplinks on my leafs for how many spines I can add. Okay, so some disadvantages of BGP and Clos. Notice that the font is very small. It's because I have an agenda. Okay, so we have our layer 2 domains, and for us, it's an entire rack of servers at the bottom here, and the top is layer 3. So if we did layer 3 in the top box and layer 2 in the bottom box, our failure domain is still an entire rack. And while that aligns nicely with our failure boundary for like power loss or some other data center issue, I prefer no failure mode to a nicely aligned failure boundary. Okay, so then another problem with this scheme is how many IPs will this rack need? Predicting the future is hard. Don't do it if you can think of another way. So if I'm in IPv4, it's a very difficult decision. I could say, okay, I'll just use IPv6 and put a quintillion IPs per rack. That's possible with IPv6. But then, as Roman mentioned, we can't move servers, VMs, or services between racks without changing IP addresses. For us, this whole network refresh came in the middle of a data center move. So we already had a lot on our plate. And going to pre-allocated rack IPs would have added another fairly hefty to-do list, or to-do item on our list. So we look for a way to not have to do that on top of everything else. Oh, also, my favorite one is when we're moving this stuff, how do we know our developers didn't hard code an IP address anywhere in our stack? I don't, so I'm going to keep them the same. Okay, so radical thought, put layer 3 everywhere, except for out-of-band management, because IPMI won't play nicely with this whole radical thought thing. IPMI is not about being radical. Okay, so also this wasn't my radical thought. It was first proposed in 2012 in an IETF draft by Peter Lepikoff and RF Premji, I think a Microsoft employee and maybe a Cisco person. Credit to their employer. So now we have the entire data center talking layer 3. So I can put 10.0.1.1 in any of these racks and move them around as I see fit. So I got to keep our legacy IP numbering scheme to make our lives easier in this data center move. I can live migrate virtual machines around. In our case, we do that with KVM, just vanilla KVM, and maybe a sprinkling of libvirt. And so we just have a bridge device on the bare metal server that gets created for every VM, and then the VMs talk BGP, and the VM server running KVM talks BGP and rebroadcasts those routes out. So we can still have fun VM stuff happening without layer 2 emulation, which is a thing that people do, but I think it sucks. Like VXLAN, for instance, there's some other harebrained schemes out there that we get to avoid entirely. And when it comes to troubleshooting, we can use our handy-dandy tools that we use every day for other stuff now to give us visibility into our layer 3 network. Something we don't get with layer 2 because it's invisible to the servers. The servers have no idea the magic that's happening to route their packets around the data center in layer 2. So you can't ask a server, hey, can you send this packet to my buddy in a different rack and tell me how it goes in that scenario. In layer 3 everywhere, you can do that. So we have MTR from server 1 to server 2, and I first go to leaf 1, then I jump up to spine 1, then I go down to leaf 2, then I go to server 2, and I have lots of nice stats to tell me what's wrong and figure out the problem. we can do BGP commands directly on the server. So I can say show IP BGP summary, and server 1 tells me it's connected to leaf 1 on ETH0. Very helpful. I don't have to trace a cable. I don't have to look at MAC addresses. I don't have to suffer needlessly. Another nice thing in this scenario is that that same address advertisement enables IP flexibility. That enables IP flexibility also does failover for stateless services. So I can have two servers, both advertising 10.0.1.1. And if the red one goes away, the blue one will pick up the traffic. So, you know, stateless things such as load balancers, DNS, NTP, VPN tunnels to other data centers, etc. You get that for free. Okay, another advantage of this scenario is we replace STP, LACP, MLAG, Linux bonding, all goes in the trash. Let's count them, 4 protocols that we replace with one protocol, which is great because I'm getting older and I can't remember shit. All right. So how long do you want to be haunted by layer 2? Not long, because public clouds don't really support it. So if you have some app that uses some layer 2 feature, now's the time to find out. And get rid of it so that you can run it in Amazon or GCP or whatever that Microsoft one is called. Okay, so if you're like me, you're probably wondering if there's any drawbacks to this design. Well, speed isn't one of them. The routing daemon, which in our case is Quagga, which I'll talk about in a bit, learns routes from its peers and programs the kernel. So on the host, the kernel does not have to consult with a user land application prior to sending out packets. We use just a tiny amount of RAM on the host since we only store 2 routes per connected leaf. One is the default route, and the other is a /8, which is routable in both data centers. So very tiny amount of routes on the hosts. All right, so that's the why of our data center design. And now I'm going to talk about how we did it. So as I mentioned, we use Quagga for layer 3 routing. And our version of Quagga has some vendor-specific tweaks that maybe someday we'll get into Quagga, but people by and large gave up on waiting for that to happen. And so they forked free-range routing, or FRR. So FRR has a ton of industry support from network names you know. And it's a Linux Foundation project. And so it seems like a safe bet, and as we upgrade, we'll be upgrading to FRR. Some of the specifics about hardware and software. Top is the spine switch, bottom is our leaf switch. We have our Linux operating system vendor, Cumulus Linux, that runs on these switches, and the hardware is made by Penguin. You can buy the hardware from lots of people. HP, Dell, Facebook's Open Compute project makes a bunch of Cumulus Linux compatible hardware if you're into OCP, which I think is kind of cool. And so a little bit about Cumulus. It's a Debian-based Linux distro, and Cumulus has written a driver so that the Linux kernel can talk to the switching ASIC. Which in our case is made by Broadcom. So the switching ASIC is kind of like the data plane. That's where all the packets are zipping in and out of the data plane. And Linux is kind of like the control plane. So I can programmatically update the ASIC using just regular CLI Linux commands. As far as the CPU architectures, you can buy RISC, you can buy ARM, but we chose x86s so that our switches can run the same exact binaries that the rest of our infrastructure runs. So things like our Datadog agent, CheckMK, which is like Hans can tell you what that is, I don't even know. Some bastard Nagios thing wrapped in an enigma. But it's useful. It works well. And And it runs just fine on this hardware with no cross-compiling, which will make you cry. All right, so we've added a bunch of complexity. Luckily, Cumulus supports all of these things: Ansible, CF Engine, Chef, Puppet, SaltStack. And we need it because we have more config to configure. We need a tool to help us handle that, and we were already using Puppet. So it was a natural next step to have it take over the network. So what are Puppet's new responsibilities? The Linux network interface configs and Quagga configs are now coupled on the servers. The servers and switches are coupled at the port assignments, and we need bridges that match individual VMs on the hosting hypervisor, along with Quagga running everywhere in order to maintain network connectivity. So here's some of how we do that. We use Puppet's Hiera data store and a custom Python build script to adhere to the dry principle, don't repeat yourself, DRY, and that has our network config data. Another objective was config files that are edited by humans should be as short as possible. If you're unfamiliar with a Hiera config, the first data source in the hierarchy section, this is just YAML, you've probably seen YAML, the first section gets priority, and the DC nodes generated is actually, that file is going to be built by our Python build script. If a given node has children, I'll explain more about that on the next slide. If it doesn't exist, Hiera just moves down the line until it finds relevant key value data for that host. Host can be our spine, can be our leaf, or it can be our servers. And every server will have a Hiera file which defines its IP address, ASN for BGP, its network interfaces, and its switch port assignments. Cool. So when building this data model, we continue to think about our network as a tree with the spines at the top and the host at the bottom. And we constructed our config files based on parent-child node relationships. So humans only need to supply static configuration for the IP, ASN, network interfaces, and switch port assignments from the child's perspective, or looking up the tree. So a typical server is the most common type of child, and its Hiera file contains the host name and switch port assignment of its parent nodes. The build script will configure the parent's config relative to its children, or looking down the tree. So we never have to edit a parent's config when children come and go. So this is what a server config looks like. So we give it a default IP. We define the loopback address. We define the network interfaces, P2, P1, and P3, P1. We really like dry. We used YAML anchors here to avoid typing things in twice. So then we configure BGP. We give it an ASN. And we tell it who its parents are, rack 1 leaf A and rack 1 leaf B on those switch port 33. So the leaf switches have parents and children in this tree, but like the servers, humans only need to define the leaf's relationships to its parents, which is a host name and switch port assignment. So parent R1 spine and another parent on switch port, switch port 49 talks to R1 spine on its switch port 45, and switch port 50 talks to its rack 2 spine on its switch port 37. So the spines have no parents, so they need the least static config, at least if you're talking about BGP stuff. We still talk to our ISPs over layer 2. That's changing soon, going to use BGP there as well. But if you're looking at a spine, it's very, very short because it has no parents, and the build script will construct all the rest. So back to infrastructure as code, another one of our buzzwords that we try to live by. We've given Puppet some very important work to do, and to safeguard the continued operation of the network, we put the Puppet code and data into Git. And this is a screenshot from GitHub where the code ends up. So we added automated testing like syntax checking and linting to make sure that there's no like dumb problems in the YAML or stupid Puppet isms that we got wrong. And then we add code review so that anyone on our engineering team, in theory, can write Puppet code or config data that changes the network, but only members of the system engineering group can approve the pull request. So that's one layer of accident prevention there. So we put all of this together, and we've been really happy with how it's been working at Shapeways. And just to summarize, running over a year in our primary DC. Oh, look, that just changed. Running for over a year in our secondary DC. Puppet configures new or reconfigured hosts. Datadog and CheckMK monitor bandwidth and availability of our network. And we've had no outages or performance issues. God, I hope this is wood. No, it isn't. All right, who's on call? Sorry, Hans. Forgot the block of wood. Okay, so Tales from Production. This is one of my top 10 t-shirts, by the way. If you want to thank me for this speech, you can buy me this t-shirt in a size medium. Okay, so the closest we've come to an outage, network outage, was when our Puppet master had a race condition, which handed out an incomplete config file to a spine in our secondary DC. That generated file that was built by the Python script was empty, as well as a lot of other. No, it was one file. Yeah. Yeah, right. The spine had no children. That was the problem. Oopsie. So the spine was knocked offline, and we looked into it and noticed that we had a race condition in how Puppet Master was getting code updates. So we fixed that problem prior to using a Puppet Master in our primary data center, and that problem was solved. The second closest we've come to an outage was when we rolled out the new network in our primary data center, which was mostly inactive at the time due to the move that was in progress. And there was a firmware bug in the leaf switches that kept knocking them offline. So Paul and I, busy like plugging in lots of cables and labeling things using our OCD powers for good. And we had only started recently to like replicate data from our then Eindhoven data center to our secondary, which was in New York. And so we weren't paying attention to monitoring, or because we weren't really there yet. And every once in a while we'd look up and a leaf switch would not have any lights on and no blinking, which is bad. You want the blinking. And we'd be like, oh, I don't know what's going on. And we'd reboot it and move on. So eventually we were like, hey, have you noticed that how the leaf switches keep turning off? And it kind of got the wheels turning. And like, oh, right. Yeah, no, that's not good. So it turned out that there was a bug in the BIOS settings that from the hardware vendor, just chose the wrong timing for the ASIC that was on the PCI bus. Like it had bad timings for the PCI bus. So it was kind of cool to like hold down delete to like go into the BIOS of a switch, and you're like, oh, I'm on a PC. Really, it's really a computer. So what's interesting about both of these stories, I think, is that the Clos topology did what it was supposed to do. We didn't notice a network outage. We had a monitoring event, and then we're able to fix the problem prior to network outage happening. All right, so what's next for us? Cumulus Linux has a really cool thing called Cumulus VX, which is a virtual machine image that you can run in Vagrant. It works with like VirtualBox and KVM and some other stuff. So what we're doing with that is we're building an entire kind of microcosm or facsimile of our production network entirely just on a laptop. And it's got 2 spines, 2 leafs, 2 Ubuntu servers, and 2 different virtual racks. And this will allow us to test updates to key components such as Cumulus OS itself, such as upgrades to that, Ubuntu, such as upgrades to that. Puppet, like we can test new versions of Puppet. Someday we may decide to actually run our Puppet code on this prior to putting it on a production network and having it change real things. Yeah, this will probably help us avoid some outage someday. The trick is to get this working before that outage. I don't know when that outage is, so we should hurry. Okay, so we can continue, if we go down this road, we can continue to make the simulation higher fidelity. We can add web servers, we can add load balancers, we can add databases, and we can, in a world where we had unlimited RAM, test even application developers' code changes on this thing. And we can say, yeah, it works on the whole stack all the way down. But that sounds crazy. Well, not crazy, just like it would take a long time. Developers. Don says awesome. Okay, we'll go with awesome. All right, so then you can get out your Xerox machine and you can copy these imaginary data centers, and you can have multiple of them and test even more stuff like your data center interconnects, your VPNs. Currently, one of these little mini data centers takes up about 6 gigs of free RAM for one data center, 12 for the two. So it is actually feasible to do this on a MacBook with enough RAM. Cool. So one thing that got more complicated, and it took us a while to actually get around to simplifying it. Yes, that's uncomplicating. Antonyms for the English majors in the crowd. So provisioning was hard. We made it easier. It's hard because when you plug in your server to the Leaf, if it doesn't have Quagga on it, that's it. Done. You're not talking to anyone else. So for a while, we had servers going out through the management network, which is still layer 2. And we cheated for a while. But then we still cheated by putting layer 2 on the Leafs and just turning it on and off with Puppet. So Puppet can turn an arbitrary port into a layer 2 port, which then can go out through the management network. You can install stuff, and then you tell Puppet you're done, and turns that port back into a layer 3 port, and by then hopefully you have Quagga. All right, we did it. We got to the end. So that's what we think a Google scale multi-million-dollar data center, billion-dollar data center, looks like at 3 racks. So any questions? I'm going to drink this beer while you guys think.
Anyone? Questions for Martín?
No good can come with this. I know in the past you've talked about being able to actually provision the switches from the ground up so that you don't even have to put configuration on them, literally just sort of net booting those. Do you see that happening anytime soon? Is that on your roadmap?
We have done it in the past. Cumulus and the hardware support something called Oni booting. Oni booting is a lot like Pixie booting with some extra stuff. Yeah, it works pretty well. If you know Pixie booting, you know Oni booting. And then it has the additional step of running a script afterwards, which you install Puppet and stuff so that you can get real config to get Quagga working and then up and running.
So on your description of Clos, I think you had the disclaimer that it doesn't work out of contained networks.
Out of what kind?
You said you can't manage IPs outside of the closed network, right?
Are you referring to out-of-band management?
Yeah, out-of-band management, right?
Yeah.
So,
that's layer 2 only, unless someone knows a cool IPMI trick that I don't know.
Okay, so overly, how do you manage things like your addressing? Like what do you use to manage your IP addresses?
So for either hosts or spines or leafs that need IP address, which is all of them, we have a static range and we allocate from that range, and we'll put that config in the YAML file that I showed. For a given machine, when we provision it, we'll assign its IP there. But that's different from the out-of-band management. The out-of-band management IP, I don't think we have that automated at all. We do or we don't? Hosts we do. Okay, so Puppet will set, Puppet, right. For a host, a Ubuntu host, Puppet will configure IPMI based on the IP we give it.
So and I know you've talked about this before, but in the config files for the switches, for the servers, and so on, you have loopback addresses. You don't have any port addresses. And so, how are you handling
the BGP side
and so on?
Yeah. Okay. So we use a feature of Quagga, and I think this is definitely working in FRR, maybe working in open source Quagga. We use like a vendor-specific Quagga that has this possibly added, but we use BGP unnumbered. So Quagga actually uses an IPv6. It's like the auto-assigned IPv6 space. So, like if you have an IP v6 interface, you magically get one of these IPv6 addresses, and then BGP unnumbered says, I'll peer with anybody who I can talk to. I don't need to know the ASN of the other side. And so because these are all point-to-point links everywhere, that's not a problem. So it could be a problem. There are other tools that we have at our disposal, like LLDP, to verify that we're plugged in where we think we're plugged in. We can have monitoring, or we could do things to prevent those links from being turned up. But BGP unnumbered just says, if I can talk to BGP on the other side, I will, and then I'll rebroadcast. So that's like a huge chunk of config that we don't ever have to think about.
It simplifies everything greatly compared to some of the stuff that was being talked about earlier with you have to track all these things. You don't have to worry about any of that. So
right, we don't have to track that. The only thing we actually have, we use private ASNs. The only thing we have to track is that we don't have two hosts that are peered with each other with the same ASN. We can reuse ASNs, with that one constraint.
And the peering on the BGP side it'll peer with anything, but the way that Puppet builds the configuration, because it knows what the routes are supposed to be advertised in both directions, configures both the server and the switch port as complements of each other. So if you have a server that's supposed to be in the DMZ and you're to plug something into it, plug it into a different port or whatnot, the switch is going to be configured, is not going to accept the routes that are coming off a machine it's not expecting to be there. If the two machines happen to be in the same network and that's what they're advertising, then it'll work. Something else, some other scripts checking or LDP checking and saying, oh, this server is actually in the wrong port, but everything is working because all of the networks were compatible. But if you plug it into an incompatible port, it just won't accept those routes. So it's not just because it'll peer sort of with anything, it doesn't compromise from a security standpoint. You have other layers that you can do that. And if you want to go a step further on the switches, it's just IP tables. So you can install IP filtering on all those ports to say, I'll only allow exactly what I expect to be there if you want to go that far into, or that fine grain level of control on there.
Any other questions? Oh, just stretching.
So in your diagrams, you're only showing like a single top of rack switch. Do you have your server setting up so they only have that single connection for your normal network?
The diagram was simplified. So we actually have two top of rack, which are our leaves in this case.
And so for that, are you doing like this topology as a multi-level, or is that something more traditional for the rack topology?
So are we doing multi-level Clos?
Yeah.
No, we're not.
Okay.
yeah, we just have those two levels of leaf and spine.
All right. Thank you.
Yeah, and if you've ever seen like the Google white papers on their Clos, they have like an infinite variation of Clos. So they'll have like 3-layer, and then they'll have 4-layer, and then they'll have weird permutations of things. So like this is kind of interesting because this is like the smallest possible Clos you can have, and you can grow from there.
Any last questions? All right. Well, thanks to our two speakers for their talks tonight, and thank you all for coming. The bar will stay open for a little bit longer, and there's enough queso for like at least 75 more people. So please keep eating. And thanks again. Let's give another round of applause to our speakers.